In this lecture, I'm going to basically give a little technical introduction to the course Optimization Theory and Algorithms. And in this lecture, these are the three topics that we will cover. We will discuss the application and scope of optimization and what necessary background is needed. We will try to pinpoint the topics that will be expected as the background in the student. And briefly, we will talk about the historical development of the field. Optimization problems appear from several sources, several origins, and in several ways. First, there are explicit optimization problems, those problems which come already tailored in the form of minimize this or maximize that, something like that. Okay. So for example, shortest, quickest path problems, design problems where you would like to minimize cost, maximize profit, or maybe maximize power to fuel consumption ratio or some such thing. Cost income minimization, maximization problems. So these problems, when they appear, it is very clear to everybody that this is an optimization problem. Then there are disguised problems which do not appear as optimization problems, but you can make a nice optimization formulation of it, and then you can solve them smartly. And these are the tricky ones in the sense that to begin with, nobody will tell that this is a problem in which you need to minimize this thing or maximize this thing. You have to work out the connection. Okay. So for example, equilibrium is a problem in which you try to find out the configuration in which the forces are balanced. Nothing to talk about minimum, maximum, or whatever. But then if you go properly into the subject matter of the problem, you notice that such an equilibrium, such a balance of forces will take place when the energy is minimized, potential energy is minimized. Fine. So then a structure problem in which you want to find out the forces in the members of a structure. So if it is statically determinate, then you can solve the equilibrium equations and find the forces. But then there are statically indeterminate structures where the number of unknowns is more than the number of equations. And those problems can be solved by working out an energy formulation in which you try to minimize the sum total of the strain energy of the structure under the forces. And that will give you the correct distribution of forces in the structure. Then these are statics problems. Even dynamics problems get formulated as optimization problems because you then write a functional which is an integral of something related to the trajectory over time, and then you say that this integral, this functional is the so-called action, and the solution of the equation of motion will be the same as the trajectory that would minimize this action. And from there, you can solve it as a minimization problem. That is a matter of formulation. Okay. Then there are problems which are optimization problem in a forced manner. That is, nothing so natural is there to put it as an optimization problem, but there are issues with the problem itself. Say you want to build the model of a phenomenon. Okay. So you try to express it in the form of a function in which the basis functions, some of the components of it are of known kind, and you want to find out the parameter values associated with them, which will give you the complete model. Okay. So those parameter values you don't know and you want to find out. So you collect a lot of data and then you try to find out those values of the parameters with which the mathematical model will match the experimental data best. Now, best brings you to optimization. You will somehow model the error in the mathematical formulation and the experimental results, experimental data in terms of those parameters. And that will give you the function that you want to minimize. The master error function you want to minimize with respect to those parameters. The corresponding values of the parameters will give you the model that you are looking for. Then there is a problem of redundancy resolution. A body can be controlled by several actuations, and say you have 8 actuations to control a particular body in space or in any set of parameters that you want to control it. Now, perhaps less number of actuators would be enough to control it if you had the system designed like that. But then there are more inputs in your hand, and therefore you can play around with those inputs. Okay, so you can load one of the actuators less, you can put some load somewhere else. Now, which way we should actuate our actuators so as to drive it? There are thousands and thousands of solutions. Now you want to resolve this redundancy. So this is actually forced in the sense that you wanted a solution, then just because redundancy is there, the advantage of which you can take in some manner, you have to define in which manner to take the advantage. You have to define the objective which you want to minimize. Then the rest of the requirement will go as constraints and you will put something to minimize. So that way, for redundancy resolution, where limited task can be fulfilled by a superabundance of resources, so which way should we use the resources so as to maximize something? And this kind of problems are redundancy resolution. Then there are problems with impersonated objectives, in which to begin with there was no objective. Okay, you just wanted to satisfy certain requirements. Now those requirements perhaps you have written in terms of equations and inequalities. Okay, so for example, in the plane there is a region and you want some point in that region, any point would do. Okay, so the region is described by certain constraints which you have to satisfy, that's all. Now there is no standard way to find one solution out of millions in which in a continuous set of solutions there is no sensible way. You can hit one and succeed, but nobody knows whether you will succeed. Okay, though there are infinite solutions, but there is no guarantee that you will get one if you just randomly hit. Okay, so that is a little awkward. But and then there is no systematic method to solve that without the optimization kind of formulation. Optimization framework offers you to define something that you want to minimize and then say minimize this thing subject to the entire description of the region you put as constraints. Okay, so this is impersonated objectives. And after you have solved like that, found one solution, and then nearby you get other solutions, which for the time being are at par with the solution that you have found, because you have minimized a useless fictitious quantity in a way, in a manner, which is not of great significance. But from there, sometimes you can reach out and define newer problems, which then give you something worthwhile to optimize with the same constraints in doing a nearby search. So there are several kinds of problems, several ways in which optimization problems crop up in science and engineering. Now, after all, optimization methods are tools. So the question arises, when to learn this subject? Now only, or if you need it? Now, here is the issue. Without a prior background, it is very much possible that when you encounter a problem, you don't recognize it as an optimization problem. And you are unlikely to formulate it as an optimization problem if you don't know any way to solve it. Okay? So you will never recognize a hidden problem, hidden optimization problem, and you will never look at that formulation if you do not have a prior background. And you will not even know what you have missed, okay, that you can go and find out. So even now, if the problem is explicit optimization problem, then what people do, who those who do not know optimization methods, they typically try to make quick shortcuts, because at that time they are not very eager to spend so much time in learning the new subject and solving it. Okay? I have found in published papers of different fields some childish suggestions of randomly sampling at 6 points, and whatever is found best, that reporting that as optimal solution. That is not the optimal solution. That is a good solution out of the 5, 6 that you tried. Okay. Then there are even more childish suggestions that in the design space, in the solution space, I go on evaluating over a discretized grid and whatever turns out best. But that is, extremely time consuming and actually meaningless. Okay. The third alternative, which people are nowadays often trying, uh, is less obvious but quite damaging. And these are the modern evaluationary algorithms, which are from the point of view of CPU time, from the point of view of computation, and the amount of your effort that goes elsewhere away from your field is enormously wasteful and often disastrous, because that drags you away from your actual field. So that is why I typically do not use evaluationary algorithms. Then there is another alternative, which is a little smart, which is using a library subroutines to solve the specific problems, just like a numerical analysis problem. Okay. After all, optimization is numerical analysis in a way. This is acceptable depending on the library that you are using. And even there, you need to know the sense, the meaning of the solution. And that is why, even if in future, in your actual problems, you call library subroutines to solve your problems, you should have a background of the problem solution, what it means, etc. So the best thing is to make an early development of the background that will preempt any future need. In that case, whenever you come across a problem, you will spot it. Okay, that yes, there is a good formulation there. Once you make the formulation, you can then revise the methods once more, the methods that you learned once earlier, and then make a good job at solving it. Okay. Now, what are the necessary background knowledge that you need for this? One is linear algebra. To begin with, you need to know the meaning and sense of the solutions of this system. Certainly when the matrix is non-singular square, even when it is rectangular, even when perfect mathematical solutions don't exist, or there are infinite solutions, even in those situations, the broad understanding you should have. Ideally, you should be in a position to solve them as they arise. Then quite often in following the analysis, we will need block operations with matrices. For example, for this assembled matrix vector equation or matrix equation, you should be able to follow this kind of implications, that this means this with invertible A. Okay, so this is block operations. Then you should have an understanding of the eigenstructure of symmetric matrices. What is meant by positive definiteness? What is its criteria, Sylvester's criteria? What is a Cholesky decomposition? So such understanding, such ideas, you should be familiar with. And then sometimes you may need to work with extended transformations like this, okay, on enhanced spaces. And you should be in a position to think about its eigenstructure, okay? And then the subspaces of Euclidean space and projections on them, such senses you should be able to work with. I'm not telling that you need to be experts in all those things, no, but you should have the geometric feel sense of those things. Then in multivariate calculus, you need to know a few things which come all the time. First, Taylor series, this almost everybody knows. And then if this is infinite, you see. Now, if you want to cut it somewhere finite without ignoring the later terms, now if you remove the dot dot dot, that will be truncated Taylor series. Okay. But then you are ignoring something, bringing in some inaccuracy. For computational work, for calculations, that is all right. But for theoretical development, you need to cut down the number of terms, yet not lose anything. So for that, you have the Taylor's formula in the remainder form. Okay. So that says that the same thing is like this, like this, like this goes on. And the last derivative is not evaluated at x naught, but somewhere in between x naught to x naught plus delta x. Okay. This is the remainder term. And Taylor's theorem says that there exists such an x bar in this interval. Okay. Extension of these notions, Taylor's series, Taylor's formula, etc., to a vector function is immediate, straightforward. On each of the y1, y2, y3, y4, there will be one such formula. So it will be a vector formula. So rest of it is same. Okay. Now, that was vector function of a scalar variable. Okay. Now we are talking about scalar function of a vector variable. Okay. In the last slide, I talked about scalar function and vector function of a scalar variable. Now we are talking about a scalar function of a vector variable. Okay. X multivariate problem. Okay. Multivariate function. So here the task of the derivative is done by the gradient. Okay. And task of the second derivative is done by the Hessian matrix, which is this symmetric matrix. Okay. And for that also you write Taylor series in this manner, similar terms. Okay. And Taylor's formula in a similar manner here. This x naught bar is between x naught and x naught plus delta x. Okay. So that is this. Okay. Then you talk about vector function of a vector variable. X is vector, f is also vector. And then the job of the first derivative is done by this Jacobian matrix. And the Taylor series truncating to first order brings you till this point, and then there are higher order terms. Now, if you want this to be up to second order, then writing that in this equation would be a little troublesome, because here itself it was a matrix. Now here it will be a little more monstrous things. So, but with the summation convention, sigmas, you can always write it. Okay. So the first order term, then the second order term. Okay. This is summed over I and j both. Fine. Now, another very fundamental thing, that is chain rule of differentiation, is often found useful in the development of optimization theory. And so I'll just remind you about what in that is likely to appear in our discussion. So for Z, a function of y, where y itself is a function of x like this, when you try to find out dz by dx, then chain rule says you say dz by dy into dy by dx, which gives you like this. Similarly, you can define a second derivative, which comes a little awkward, but you can always fill in the logic and get it. Okay. Now, if z is actually a function of x and y, in which y itself happens to be a function of x, then ultimately z is function of x only. Okay. And then you want to find out dz by dx, and there one component in the derivative comes directly from this x dependence, and another component comes through the dependence of z on x through y. Okay, so that actually uses a chain rule here. And this is another such situation in which this second thing, okay, this psi, in place of this psi, I have put a vector function. So there, what will happen is that this part will become the gradient. Okay, so because x has several coordinates, x1, x2 up to xn, so with respect to all of those, you have to bring in the derivatives and put them properly in place. And this entire thing from here to here is actually the gradient transpose dx by dt. So this is a vector transpose, that is gradient transpose, and this is actually the derivative of a vector function with respect to a scalar variable, right? Now this chain rule, this kind of affair, f of something and something else through the same thing, okay, that comes in several ways. For example, this chain rule gets really involved and tricky for a function like this, where phi is scalar function of lambda, but this function is described like this as L, which is a function of lambda and x, in which x is a function of lambda. Okay, so when you try to find out the gradient of this, you have to take one component from here and one component through this. So one component from here directly is this state derivative gradient, and through this will come as this straightforward gradient with respect to x, but then it has to be multiplied with this Jacobian, okay, Jacobian transpose actually, okay, because x of lambda is a vector function of a vector variable. And in this, when you try to determine each component of this gradient vector, then one of them will appear like this, del L by del lambda k, and here all lambda i's and I not equal to k are held constant. Okay, it is with respect to this only, but x's will vary. Okay, because that variation you are providing for here. And on this side, this del L by del lambda k is with all lambda i's except k are held constant, and all xj's are also held constant. That is not only from the same family, but from the other family also. Okay, and plus here the variation of L on lambda through x is provided for from here. Actually, this summation is actually this product term. Okay, so this kind of complicated application of chain rule appears at times. Now, Jacobian of an implicit function. For an m-dimensional vector function h of a vector variable x, this kind of an equation, it is actually a vector equation, which means m equations in n unknowns. Okay, so m unknowns can be solved. Okay, so and this gives you a surface kind of thing in of this many dimensions in the n-dimensional x space. So you can partition the unknowns x into two parts. This z, which you can solve in terms of the rest of them y, in terms of which you will solve, because you have m equations. So m unknowns you can solve. So z of y is then the implicit function defined like this. And if you want the derivative of that implicit function, in some sense dh by dy or the corresponding Jacobian, you do not call it d. So then at a point which is on that surface where this is satisfied, okay, if you use the chain rule to differentiate it with respect to finally y, then you will get it like this. This is direct with respect to y, this is through z. And then from there, if you want, you can solve for this. And you solve for this, how? You invert it and multiply on this side and then take it on the other side of the equation. So you get it this. And the single variable analog of that is simply this, which you know. Okay. So from psi of xy equal to 0, if you want to find out dy by dx, this is what you do by differentiating it with respect to x and then separating out dy by dx. So this and this are actually the same thing. Other than these pure mathematics things, what else you need to know? You have to have some numerical analysis background. For example, algorithms for solving linear systems, nonlinear equation solving. Of course, these are going to appear in our course discussion also, but if you have a little prior knowledge, then you will appreciate them better. Then eigenvalue problem, it is not necessary that you know how to solve them actually, okay, on your own. I mean, like writing a program to solve an eigenvalue problem of 50 by 50 dimension. No, that much is not needed, but you have to have a sense of their um, meaning, a sense of their values and their meaning of what they mean and what way the solutions are found by whoever finds it. Okay, so you have to have the overall background, overall understanding of the eigenvalue problems. Then function interpolation, and of course numerical differentiation. So these are topics of numerical analysis which you may need. Numerical methods for differential equations you are unlikely to need in this course. Oh, yes. And it is good to have a background of a programming language. That is going to help. If you do not have, then you can also use the MATLAB Octave programming environment, but that you should be able to use properly. Okay. And what happens is that many times people who take this course, along with the course, they concurrently also develop some programming skill. Okay, so that's also fine, but it is important that you have some background of programming, or you should not have hesitation of going into programming something. Okay, and you should have access to some programming environment. Now we come to the historical development. People have come across optimization problems since the beginning of civilization. Natural interest for meeting their bare necessities. For example, shortest power path to the water source. That is the problem of geodesy. Use and trade of land, fixing revenues, required their measurements and how to maximize land areas and so on. So they had also brought in interesting optimization problems. And the isoperimetric problem, that is with the same perimeter, what is the best area? Okay, so that problem is very old. Okay, and thousands of years old, to the extent that in the epic Aeneid by Virgil, there is a there is an interesting problem of that kind which came up. No? So then the calendar making also brought in some optimization problems. For example, modeling correctly the solstices, which are actually the longest day, shortest day kind of problems. Okay. one contribution of Hieron of Alexandria, that was before Christ or just after Christ, uh, that in a way also anticipates Fermat's principle on reflection. So these are very old developments. After that, during the medieval period, several Arabic Persian scholars also entered the field and made contributions. But we make a long jump and start from the modern times. Uh, Kepler actually, apart from his planetary exploits, he actually gave rise to a very interesting optimization problem, which is now known as the secretary problem, which later got developed into the field of dynamic programming. And Fermat's contribution was also very important. In a way, he anticipated calculus. Just before Newton and Leibniz, his contribution in calculus and maxima and minima actually were a little before Newton and Leibniz. And then, of course, immediately after that, Newton and Leibniz properly developed calculus with tremendous effect on optimization, because nowadays most optimization formulations talk about calculus in some way or the other. And of course, famous Newton's method for optimization, that is also a development of this time to begin with. Later, people polished it, of course. Bernoulli and others started on the famous Brachistochrone problem that initiated variational calculus in the same century. And just the next century, variational calculus got a lot of development through Euler, Maupertuis, Lagrange. You know Maupertuis' principle of least action. And Lagrange, of course, Lagrange multipliers. In 18th century itself, Monge studied a transport problem. Okay? So how to transport things in the best possible manner among places. And that later led to the field of operations research, very important in industrial engineering. And 20th century was full of operations research. In 19th century, Gauss and Legendre developed the least square problem. Fourier formulated the linear programming problem first. Cauchy developed the steepest descent method, which we will be studying. Hamilton, besides contributing in variational calculus, principle of least action, also formulated a famous problem called traveling salesman problem, which later gave rise to the field of combinatorial optimization. Around this time, Bolzano and Weierstrass developed rigorous mathematical framework for the concepts of limit, continuity, and the notion of algorithms and their convergences, which we will be discussing shortly. Jensen and others around the turn of the century developed the convexity theory. In early 20th century, a curious development took place. Somehow, at some time, the odd term mathematical programming gained currency for the theory of optimization. And later it created confusion with computer programming many times. Okay, but no, that is a mathematical framework of solving optimization problems. That was called mathematical programming. And from this basis, actually, several particular subfields in optimization got funny kind of names. Linear programming, non-linear programming, quadratic programming, convex programming problem, integer programming, mixed integer programming, geometric programming, dynamic programming. Such names came basically from this peculiar use of the word programming. And the time when mathematical programming term came, at that time, there was no business of computer programming, okay, because computers came later. And so that is how the confusion is created. In the 20th century, um, yeah, then in 1917, the first textbook of optimization came up. and by Harris Hancock. Menger developed a general formulation for the traveling salesman problem, which was earlier formulated by Hamilton. Kantorovich gave a linear programming model in 1939, and von Neumann, just after that, presented the duality theory, which turned out to be immensely useful. And Danzig developed the simplex method of linear programming problem. These developments we are going to study. Markowitz developed a famous portfolio theory, which actually contained the quadratic optimization problem, the model of the quadratic optimization problem. The rest of the development of the nonlinear optimization problem in 20th century is what this course will be about. Karush Kuntukar developed the first order optimality conditions for nonlinear optimization problems. Then in parallel, two groups developed two families of methods, conjugate gradient and Quasi-Newton methods. And then in 1960s and 70s, the other nonlinear optimization methods were developed by several groups, Zautendijk, Rosen, Hestenes, Wilson, and several other contributors. Among other developments in 20th century, Bellman developed dynamic programming, Zener developed geometric programming, Holland and others started working on population-based evolutionary methods, on which later many others also have contributed in last 3-4 decades. Karmarkar gave a polynomial time algorithm for linear programming problems, which brought the interest of the scientific community to integer point methods for linear programming methods, in a linear programming problem also. And then several researchers in the decades around 2000 on both sides of the turn of the century concentrated a lot on difficult problems which could not be tackled with the computational power of earlier times, like multimodal problems, multi-objective problems, stochastic optimization, game theory, etc. And of course, along with that, a lot of old wine in new bottle is getting served, because right now, which development of this time, which is the current time, is going to stay is not clear. Okay. So these are the important points to note. Lot of application in all fields of science and engineering, particularly hidden problems for which you have to have an understanding to begin with. And to master the subject, one needs a good background of applied mathematics and programming. And other than the mainstream optimization problems, there are many other problems around on this side, that side, this kind of problem, that kind of problem, that any exposition or discourse will cover only a part of it. So we will try to cover in this course the mainstream problems of optimization primarily. Okay, and only we will take some time out to talk about the fringe issues. Okay, next lecture topic will be optimization problems, kind of problems that we will talk about. Thank you.